Hello and welcome to the 7th lecture of Introductory Astronomy. So today we're going to do the Earth and the Moon. So many of us are already somewhat familiar with at least a small patch of the Earth. So you might recognize that this is the Earth on the What Is It slide today. What is this slide? And we'll be talking about exactly what kind of Earth this is. This is an email attachment of phenomena, so I don't know if many of you have gotten this over email, but I'll talk about it a bit, particularly at the end. So, what is this? This is Introductory Astronomy, a course being taught for credit at Michigan Technological University. The phone number is PH1600. PH stands for physics. So this is taught inside the physics department. So we are reviewing some key attributes of the Earth and the Moon today, and next time we'll be jumping out into the outer solar system doing Jupiter and Uranus, possibly Neptune. So if you want to get credit, you want to go to courses.mtu.edu, and this slide will exist in every lecture. And here's the other slide that exists in every lecture. They're a match set. It's illegal to separate them. So you're responsible for the lecture material. That's your best bet. So watch this lecture and have fun. And then wake up and then rewind it and have fun again. So you're also responsible for listed Wikipedia entries, but not the higher math. They go off into some strange integral or differential equation. Don't worry about it. You're responsible for the subject, the general ideas there. You're also responsible for the astronomy pictures of the day shown every day. So I will review them at the end of this lecture for this past week. And one of the reasons why I do this is because I am one of the APODs, people who create the astronomy picture of the day. So I know them pretty well. And also the familiarity helps me make this lecture more beautiful so that you can see the amazing sights of the universe right on your monitor while staying awake. Again, if you're interested in credit, then you need to enroll at Michigan Tech, which can cost money, except I think if you're over 60 and live in the United States, possibly in the state of Michigan, I don't know, then you can take this for free. But you would need to complete the quizzes to get credit, and you'd have to log in through the Blackboard system to see the quiz questions. But if you're just interested in knowledge, then just watch the lectures. Two simple Wikipedia entries will be ruling today. One is Earth and one is Moon. These do coincide with today's topics. We had this slide last time, so this is shows a little bit about the Earth. So the Earth is the biggest rock in the inner solar system. Biggest rock in the solar system. It's bigger than any moon. It's bigger than the other rocky planets, which are Mars and Venus, slightly bigger than Venus. And this is where they play Major League Baseball. The only planet known that is known to happen. This is one of the most famous pictures of modern times, voted by Time magazine's editors as the picture of the century for the 1900s. This was taken by Apollo 8 as they orbited the moon. As they came over the limb of the moon, this is your basic moon down here, they saw this big blue marble, which is Earth. And it's famous because it puts the Earth in perspective as what it is and shows that we all live on this little rock ball with gas around it. And that the moon, however, is slightly different. It doesn't have a significant atmosphere, which we'll be talking about later. So there are actually many pictures of the Earth from the moon, and we'll be seeing another one later on. This is one of the more dramatic. This is not even the first. This is, I guess, one of the first good color ones, but it's not the first. Here's the Earth-Moon system taken from a passing spacecraft, Nozomi, which is, I think, a Japanese spacecraft, went out into the solar system. And here you can see the Earth and the Moon. Many times the Earth-Moon system might be considered to be a dual planet system because the Moon is large compared to the size of the Earth. There's no other planetary system that we know of where the Moon is so large a fraction of the main planet's size. This is probably the most famous picture of the Earth, taken by the Apollo 17 crew. Also, many of the images of the Earth are called Big Blue Marble. Many times, if you see in the literature a picture of the Earth, it is this exact one. And if you want to read a little bit of history of that, you can go to this APOD and the links inside. We've highlighted this several times. So this is Africa and Madagascar, the Arabian Peninsula. And here's Antarctica. And there are all kinds of clouds around. And it's just a picture that's so common and it's so public domain that just gets reproduced over and over. What color is the Earth? There's lots of places where it's mostly green due to vegetation and trees. So where we are here, lots of trees makes it green due to the chlorophyll and photosynthesis in the trees and plants. There are parts of the Earth that are not very green. For instance, there are oceans, and the oceans are water and mostly, well, because if you look through enough water, it's blue, but not this dark blue. Also, they reflect some of the blue of the sky, so the oceans are shown in blue here. Here we have a big desert. This is the Sahara Desert, so there's not lots of vegetation there. It's basically the color of the rock. Much of the Australian outback also does not have a lot of vegetation. But some of the Rocky Mountains of the U.S., here you see the Himalayan mountains here. But most of the eastern seaboard of the United States, where there's lots of population, much of the western seaboard, much of Europe, Japan, the Amazon, lots of vegetation. Parts of Africa where there's the lions and the tigers, lots of vegetation there. As we go up here, we see there's ice pack in Greenland and Iceland, where it's essentially frozen much of the year. So what about this Earth? What is it? Well, we live on the crust. And above the crust, there's atmosphere. And the atmosphere is constantly changing, and that's causing erosion on the Earth. And it's possibly this constantly changing thing in the water which allows, and the oxygen, which allows there to be life on Earth. So you need life, you need oxygen for life. And water also greatly helps life. But this is the life we know. As I'll discuss in a later lecture, there might be life out in the universe which isn't relevant for that. But it seems that these basic ingredients and a constantly changing environment in some way is good for life to exist, particularly intelligent life. So we've been through the layers of the Earth's atmosphere, which I'll review again. Another slide too. Exosphere is the top, thermosphere, mesosphere, stratosphere, troposphere. We live on the crust. Under the crust, there's the mantle, sometimes differentiated into the upper mantle. There's the core of the Earth, which is molten, and there's an outer core and inner core. And I believe there's evidence that the inner core of the Earth, the core of the Earth rotates at different speed than the outside of the Earth. So I've always wondered what would happen eventually if the Earth cools enough. The radioactivity inside the Earth, which heats the Earth, reduces enough. Eventually, the Earth will lock, and we'll all be essentially one rocky part. That might be a catastrophic event in the history of the Earth. Okay, here's a picture of the gravity on the Earth. So gravity is very nearly the same everywhere you go on Earth. But if you go up high on a mountain, then you're going to see slightly less gravity. And if you go down into a valley, you're going to see slightly more gravity. But that's not the only reason why gravity changes over the Earth. Apparently, there's places in the Earth where there's lots of dense rock, particularly dense rock under the crust or in the crust, and not places where there's not so dense rock. And so, for instance, off the coast of India, there appears to be a relatively anomalous feature where I believe there seems to be a lot of dense rock. And there's other places where it seems like slightly less. So this was taken by the GRACE satellite that orbits the Earth and notices very slight changes in the acceleration due to gravity. So where do the people live? Here we see population density. The people tend to live in first of all, if you were to draw the equator, which I believe is here, which actually cuts through South America. For some reason, I used to believe that all of South America, and for some reason all of Africa was below the equator, but that's just not true. Most of the land mass is above Earth's equator. So most of Earth is water. 70% is covered with water. So that's real good. That's probably where life developed. Most of the land mass is in the north, and so this is the south. In the north, it happens to be slightly more temperate, also because in the north, when there's the most sunlight, due to the longest days and the sun being highest in the sky, we're furthest from the sun. So that makes the summers a little bit less intense, and the winters a little bit less intense. So that might be one reason. Also, there's just all this land mass there. Also, the more temperate climates tend to be near bodies of water, in particular oceans. So the east coast of the US has lots of people, as does the west coast. Western Europe, lots of people. Very much a lot of people in the eastern part of China. India has a lot of people, very temperate there. However, people tend to avoid the centers of continents. That's not true for Europe. Europe has so many people. But there's relatively few people in the western states of the United States before you get to California and Oregon and Washington. Also in South America, this is true again. Many people in the densely populated areas of Brazil and Argentina, and relatively few people in the Amazon in the middle. In Africa, people tend to avoid the Sahara because it's hard to drink things there because they tend to evaporate, it's being so hot. Big open area in the outback of Australia. So if you want to go someplace where the temperature isn't that extreme and you don't want any people, you might try the outback of Australia. The northern parts of Canada, there's relatively few people also. It gets kind of cold there. So here we see where there's the most people. The highs and lows. Earth is mostly flat. It's a pretty good billiard ball, but it's not exactly flat. So here you see the highest mountains are the Himalayas here in Asia. There's also high mountains in Chile on the western coast of South America. We have our Rockies here in the United States, which are not completely small. And there are some depths. There's Death Valley, California. There's the lower parts of the southeastern U.S., parts of the Amazon, parts of the outback, parts of northern Europe and northern Asia also tend to be relatively low. So the Earth is broken up into plates, tectonic plates. And these tectonic plates very slowly move. So for instance, in California, there are plates that are butting up against each other. And when they slightly slide, or sometimes more than slightly slide, there's a big earthquake. There's many plate boundaries across the world. So on the time scale of hundreds of millions of years, the Earth doesn't look like it looks now. One might notice if we back up to a previous, that there's a coincidence between this part and this part. It looks to the naive person like you could take South America and just move it right into Africa and it fits like a puzzle piece. And I remember that I thought that when I was in elementary school, but they never announced that they were together way back 30, 40 years ago, 40 years ago. I'm not the only person to think this. I've heard anecdotal evidence that many, many people have noticed that coincidence, but it's one of these unspoken things. Like everyone seems to know it's a coincidence, but at that point, the planetary geologists of 50 years ago just didn't think that that was a good theory, that the Earth pretty much looked always the way it was. But now we know that over the time scale of hundreds of millions of years, yes, you can break off plates and things can move. And once, yes, South America was adjacent to Africa, and animals could just go across. So, to some degree, the continents of the Earth are a bit like a puzzle, and you can see how they matched up. So they will match up again. Once again, South America will go and meet up with Africa, but only, here's better news, North America will meet up with Africa too. Based on these computer models, so don't hold me to this, in 250 million years, don't send to my future email address that you expected to be able to walk across here and it didn't work out. So this is our best guess, someone's computer model best guess. In fact, Scotese' best guess as to how the continental plates will move and how the land masses will line up in 250 million years. And this is sometimes dubbed Pangaea Ultima. So there will be one large landmass. Antarctica and Australia will merge. Europe and Asia will merge. North and South America will merge. The Americas will merge with Africa. And there will be this unusual sea here. So things are always changing. And even though things only move on the time scale of millimeters a year, that adds up over millions of years. And you can move thousands of kilometers in that time. Okay, a little bit on the Earth's atmosphere. Again, we see what happens in different parts. Above maybe 700 kilometers is the exosphere. In the thermosphere is where the space shuttle flies, and the lower part is where the aurora flies, between maybe 80 kilometers and 700 kilometers. Then you have your more dense atmosphere, so the atmosphere becomes more dense as you go down. Actually, the temperature inverts a couple places, so it's not clearly monotonic. Meteors burn up between 50 and 80 kilometers. Weather balloons and such will fly between 20 kilometers and 50 kilometers. And finally, large mountains and even airplanes will fly up to about, well, much less than 18 kilometers. So what's our atmosphere made out of? Our atmosphere is mostly nitrogen. It's really small, so N2 is what that says, and it's about 78% nitrogen. Nitrogen is important for life. It is considered, though, to be secondary in importance to oxygen. So many times for things to grow, it needs nitrogen, which is why you put down organic things, because they have nitrogen that it can use. There's nitrogen right in the air, but many things can't use the nitrogen. Many living organisms can't use the nitrogen in the air. Oxygen is important pretty much for almost all living organisms, certainly all animals. So we need oxygen to run our bodies, and about 21% of the Earth's atmosphere is oxygen. The rest is, there's about 1% argon, and the rest is very small trace amounts. There's a little bit of carbon dioxide, neon, helium, molecular hydrogen. So the carbon dioxide that we're worried about, because carbon dioxide, we can measure it, the amounts relatively accurately, and we're worried that the carbon dioxide level is going up recently. And there's a debate as to what's going on. My guess, and most scientists guess, that humans are doing this. The worry is we'll reach, carbon dioxide reflects infrared light, so that the Earth glows in infrared, so if that's reflected down, the Earth becomes an oven. And it's like closing the oven door, and the Earth can heat up and maybe become a Venus. So Venus is not a nice place to visit. It's well too hot, and things would melt there. Mars is, again, mostly carbon dioxide. It's cold, but it didn't have a runaway greenhouse effect, at least not in recent times. So we're interested in keeping the amount of carbon dioxide relatively low. That's our snapshot of Earth today. One myth is that we understand the complete surface of the Earth. It's only other planets we don't understand. So we send spacecraft to take images, radar images of the surface of Venus, for instance, and think that, oh, good, that's the first time we're seeing it. And it is the first time we're seeing Venus. But there are things on Earth we don't understand. This is kilometers across, I believe. It's called the Richat structure. It's frequently seen by astronauts. I believe you can find it now with Google Earth. Google Earth is really cool because it's being used to discover things on the surface of the Earth all the time, too. So here we see this big circular structure, and people don't know what caused it. So there are mysteries right here on Earth, big mysteries, things we don't know exactly why they are. It is thought these are, one guess is these are volcanic domes of some sort created by volcanism and not related to a meteor impact. That's the best guess. The surface of the Earth is constantly undergoing changes, mostly by air and water. Water carves lots of channels. But we've got Hawaiian Islands that are popping into existence because of volcanoes, and we have other volcanoes going off. This one, I believe, is in Europe, and it's Mount Etna, and it looks really cool when it goes off. It's your classic volcano. So being thrown here are essentially magma rock balls. So you don't want to catch one with your glove or without your glove because it's too hot and pretty heavy, some of them. So this will create a jagged black rock surface here and create a new surface. So some of the Earth's surface gets resurfaced by magma bubbling up through the Earth's surface through volcanoes. Here's one, Alaskan volcano that erupted, visible, particularly visible from the space shuttle or the space station. So I don't know if this eruption, many times you can see them but from space. I don't know if it was discovered from space. But here you see a lot of ash come out. It's not all hot rock that flows out. Many times it's ash. Here's a really cool image of, here you see ash. Here you see just background clouds. Here you see dark, sort of frozen lava frozen into rock already. And here you see more lava coming out onto the surface of this volcano. One of the big news on the Earth is that it is no debate that the Earth's Antarctic ice sheet is shrinking. Parts break off and melt. And so large parts of Antarctica the ice covering near Antarctica is decreasing. What's happening also is that allows the ice that is on the land mass of Antarctica. So in the Arctic in the north, there's no land mass. It's all ice. So when that melts, it's not going to raise sea level that much. But in Antarctica, on the south part of our planet, there is real land. And on top of this land, there is a lot of frozen water. And that is held up from going into the seas by the ice sheets that are around Antarctica now. So when these ice sheets warm up and break off and float away and melt, it creates less of an ice dam so that the ice that's on Antarctica can now slide off of Antarctica. And when that happens, there's more water on the seas, and it pushes down on the seas. And it's not because of the pushing down. There's more volume, more water volume, and that causes sea levels to rise. So who cares if sea levels rise? Well, the higher it goes, the more trouble there is. There's already parts of the Earth, cities on the Earth, that are essentially in existence because they're able to pump water out. And if the sea level goes up, and it can go up theoretically meters, not just millimeters. It can go up meters if lots of Antarctica melts and Greenland melts. Then you start getting into problems. There are famous cities like New York City, that could end up below sea level. So it is a concern. Here's a picture taken in 2002, and all of this was ice. These are Rocky Mountains. And all of this was part of the Antarctic ice shelf. But today, only the mountains exist. This is water today. It shows the extent of the melt-off in Antarctica and why that is a concern. All right, another feature of the Earth is that it has a magnetic pole, and this magnetic pole has probably wandered about the Earth. But here at the time in 1999, the Earth's magnetic pole was in the very north of Canada and moving. I think it was moving slightly north. It was on one of the islands. I think it was on this island here. And now it's off that island and moving. I think it moves, like a sizable amount. You could watch it. If you were there and you knew exactly where the north is, you could watch it move. But I think it moves on the order of maybe 1 kilometer a year or less. So it can move off of places. The North Magnetic Pole is interesting because it's very near the spin axis pole of the Earth, and that's useful to know where the spin axis pole is. So if you have a magnetic compass, it will point to the North Magnetic Pole, and when we're down in the US and many places well south, that's very useful because that's roughly the direction of the spin axis pole. However, if you're up in this area, it's not going to be real useful. Okay, aurora, something that we see, astronomical, considered to be astronomical. This is caused by originally the sun. The sun is many times very active and throwing off stuff. So when it throws off coronal mass ejections and flares, a lot of energetic particles bump into the cloud of energetic particles around the Earth. And then those energetic particles bump into the Earth's atmosphere, fall to Earth, usually around the poles. And when they bump the Earth's atmosphere, they knock electrons from the gas in the Earth's atmosphere. And when those electrons fall back to those molecules, they emit light. So typically green is an indicator of oxygen. So there's aurora here. There's other types, other colors of aurora, other gases being excited. And here you see a meteor also. So I think the meteor is, I forget, it's below or above the aurora. Let's go back and find out. It is, missed it. It is below the aurora. Okay. Aurora, again, usually come in rings, so they fall to the Earth's, and they're channeled along magnetic field lines. Because it's hard to go against the magnetic field, it's free to fall on the magnetic field, so that's why the magnetic field acts as a funnel and a channel. Here we see auroras over both of Earth poles, taken by polar satellite. Here you can see how they change over the time scale of the Earth rotating, and the northern borealis and the southern borealis, sometimes called the aurora borealis, and there's another term for, I think, involving, well, the north and south northern lights. I'm blanking on the term right now. So let's go previous and back and see if it does it again. Yeah, so you can see how they would change. And if you go out and you can see aurora, it's pretty cool. So you can see them change on the time scale of minutes to hours, big changes on the time scale of hours. Many times people see them and they think, oh, it's a little bit hazy tonight. Up in the UP, we might be able to see aurora, well, depending on how active the sun is, maybe 30 nights a year. So you go out and you say, oh, it's a little bit hazy, but then as you notice, there's parts that seem relatively more dense clouds, but then they change, but you can always see stars through them. So that's one of the ways I know I'm seeing aurora, that I can see stars right through them, no problem. And they change unusually on the time scale of minutes. Sometimes they can be relatively bright once your eyes adapt. There are web pages where you can find out that there are auroral storms going on, and some people up here have phone trees where if they see a really cool aurora display, they'll call their friends and wake them up. They have permission to wake them up in the middle of the night, and so your cell phone goes off in the end. The message is, go outside and look up, and it's really cool to see aurora if you get the chance. Okay, this is an interesting picture that's educational to explain. So this is the space shuttle was launched, and here is the plume trail from the space shuttle. This is the space shuttle itself. So the here you see the belt of Venus. So on the ground, the sun is already set. So people living on the ground are essentially in shadow. But it's not completely dark because the Earth has an atmosphere, and there's still light scattered off the atmosphere. So above here, this part, you can see the shadow increases, still in shadow, not in shadow. Here's sort of the belt of Venus, but this is not in shadow here. That's the sunlight up there, sunlight. But the sunlight, this plume, is opaque, and it's going to make a shadow. So this was taken during a full moon. So the shadow is going to point directly opposite the sun. And directly opposite the sun, when there's a full moon, is toward the full moon. Opposite the sun and the moon are opposite when there's a full moon. So opposite the sun, that's what it's going to point. So someone took a picture right at that, and it's really cool. You can see the plume pointing right at the full moon. Okay, let's talk about the moon a bit. So humans have been to the moon. The Apollo moon shots began in '61, but they didn't land until '69. There's a very famous speech by the American president in '61. Or maybe it was 60, about going to the moon. I should remember the exact date. And amazingly, even with the technologies of the 1960s, the U.S., the United States, was able to do that. And they landed people on the moon. They orbited the moon a little bit before, and then Neil Armstrong and Buzz Aldrin went out on the moon in 1969. And the television coverage of that was amazing, and something like 1 billion people across the Earth were all watching the same thing. So it was really an international event. The far side of the moon was first imaged in 1959. And it's an interesting trivia question. When is the first time that humans did anything to hit the moon? When was the first human contact with the moon in any way? Not an actual human, but something we made. And I think it was in the late 50s when the then Soviet Union just launched a satellite that struck the moon. And didn't land softly, it landed hard. And it exploded and released many little metal objects that said CCCP. I don't know exactly where that is, but they were sort of labeling the moon back then. So the moon is something that many people see, every month, but oddly enough, it's still we're not completely sure the origin of the moon. There are many hypotheses, and there is a favorite hypothesis at this time. But one possible hypothesis is that the moon and the Earth formed, and because of the fast rotation of the Earth when it was very young, the moon broke off and then recongealed out where it is. The problem with that is, again, I'm blanking on why is that. I think, the orbit of the moon and the rotation of the Earth don't match up well enough to make that a good enough explanation. There might be ways of knocking the Earth off so the Earth's equator would not match up with the moon's orbit, but still it makes the fission hypothesis a little bit more suspect. The capture hypothesis that the moon was just out there floating around, having a good time, and was gravitationally captured by the Earth. The co-formation hypothesis that the Earth and the moon just happened to form right near each other. They formed inside each other's gravitational fields. And then the most favored one is the giant impact hypothesis, that something maybe the size of Mars hit the Earth in a tremendous collision about 4.5 billion years ago. Tremendous collision. And based on that impact, there was debris, lots of debris, and part of the debris formed into the moon, and the rest of it congealed into combined Earth. And that is favored currently, that we hit something Mars-shaped 4.5 billion years ago. I always find it's amazing that, again, here, the Earth is a common object. There's things we don't know about the Earth. The moon is a common object. There's things we don't know about the moon. There's a lot we don't know about the moon, but that's one of the bigger ones. Here's a picture of the moon from Earth. Here we see the effect of the Earth's atmosphere dimming out the bottom part, and you can see that the blue sunlight is scattered out. And it's a pretty picture. There's lots of interesting textures in the cloud patterns. Okay, so other aspects about the Earth's moon, attributes of the Earth's moon, is that it orbits the Earth once a month. So again, the moon is tidally locked to the Earth, always shows pretty much the same face. There are many craters on the moon. Again, many craters on the Earth, but many of the craters on the Earth have been wiped out by erosion. But on the moon, there's nowhere near that kind of erosion. So the craters pretty much stay. There's area where there's lots of craters, the highlands, and they're relatively light-colored. And there's area where there's relatively few, dark-colored, called maria. It used to be thought that these were seas of water many hundreds of years ago. But now we know that volcanism occurred more toward the Earth and filled impact basins with then lava, which then, of course, had many craters of their own. But they're now known as maria. So this is a lunation, one period of the Earth, the moon circling the Earth. Here you see that pretty much you can always see the same part of the moon. What's on the back of the moon, we don't know from this image. And we didn't know up until the late 50s. We didn't know. So there's some craters, a lot of craters. The dark areas are the marias. There's a dark area there. So you do see slightly different bits of the moon. If you look on the edges, there's a area that comes and goes over there. That's called the libration of the moon. So the moon doesn't exactly keep the same face, but mostly keeps the same face to the Earth. And here you see the different phases just because it's illuminated by different parts of the sun. Okay, so this is two of the more obvious craters. Tycho, you can see with even small binoculars, and Copernicus, two big craters. Again, the craters mostly are just outside the Earth, the ability of the human eye to see. So when Galileo took out his telescope, he was able to see craters on the moon. All you needed was a little bit more sight, a little bit more resolution to be able to do that, a little bit more magnification. This is the far side of the moon, not always dark, taken by Apollo 16. So the Apollos that landed on the moon were all the way from Apollo 11 to Apollo 17. Well, the 13th had to turn back, but the rest of them landed on it. Here you see the far side of the moon has more of highlands. This is highlands, and fewer Maria. These are Maria, the dark regions. So it appears lighter and more cratered. So no one in humanity ever saw that before, 50 years ago. The moon has been described as a magnificent desolation. It's mostly gray, but with a slight hint of brown. I'm told, I've never been there. So this is a lunarscape where you can see that. You can see the mountains. You can see the dark sky in the background, which, since this is so bright with sunlight, it's hard to see the stars. Impossible in the photographs, since the photographs have only a limited dynamic range. Here you see a lunar buggy that was in the later Apollo missions, and an astronaut getting on there to drive around and collect moon rocks. This is the famous first step onto the moon by Neil Armstrong. I believe that it was seen in higher resolution than the images we have today. So there is an image chase on, and one of the lost items of recent history is a high-resolution image of Neil Armstrong stepping on the moon. There was a thought, I think just a few years ago, that maybe the Australians had recorded it in their telemetry, but I think that was not found. So we have relatively low-resolution images today of Neil Armstrong making the first step onto the moon. Here is it's really a tremendous event to go out away from the Earth like that. It was thought that this would be the natural stepping stone, and we would go to Mars in the next few years after that, and then we'd be out in the outer solar system, and soon we'd be colonizing, nearby worlds. But it turned out that we have not yet been back to the moon, and there is plans on the drawing board to try to get back to the moon now, not only from the United States, but also from China and Japan. Probably Russia could attempt it. India, more and more places are becoming space-worthy. So in my opinion, one of the reasons why we went to the moon is for not only the scientific value, but for the national prestige value. So the U.S. Congress is willing to give a lot of money to maintain U.S. prestige, more than to investigate scientific things. So possibly now that prestige is coming back on the line with other nations contemplating going to the moon, maybe again a lot of money will be diverted to that. But this is the first step of a human on something other than the Earth. A truly amazing event. Humans have gotten off the Earth in the lifetimes, of your parents, grandparents. One of the Apollo 12, the second mission to the moon, landed right near Surveyor 3. This is Surveyor 3. This is one of the robotic missions to the moon that did not have people that occurred before Apollo from NASA. So an astronaut went over there. This is the lunar module. Walked over there and checked it out. And one of the things I think they found is there were some microbes that survived. So the amazing question, one of the trick questions is there life on the moon? And the expected answer is no, there's no life on the moon. But the most probable answer is yes. There's life on the moon because we put it there, and there's microbes that still survive likely even today out of direct sunlight. And the next fun question is there life on Mars? And most people say, well, it's ambiguous, but we don't think there's evidence of life on Mars. But there's excellent reason to believe there is life on Mars because some of the space probes that crashed into Mars that were launched from Earth were not decontaminated. And so quite possibly there were microbes on there that have survived. So my guess is there is life on Mars because we put it there. Was there life on Mars that developed there? That's a much hotter topic of debate. Okay, in some of the instruments on the moon are still we can bounce lasers off them and we can still get data from them, and even that, some of the data from the Apollo landings is being analyzed. So we're trying to understand moonquakes. We're finding that moonquakes are surprisingly common. And so this analysis of older data and with older instruments came about in 2006. So we're still learning about the moon even today. This is a panoramic that's digitally compressed like this, horizontally. Here's an astronaut running. If you go to the APOD December 10, people are still digging through the archives of the NASA Apollo archives and stitching together images that were not stitched together before. And you can do it much more easily now with Photoshop and digital techniques. And so here is one from, you can see moonpans.com. You can see many, many new panoramas. And these are panoramas of the moon that haven't been seen before other than by astronauts. Now, what has existed is smaller photographs, but it's kind of interesting to see them all together. And so I compress this so you can see the relative heights of mountains and things like that and rocks. Here's a lunar rill that goes across the moon. They are indentations. They cross craters sometimes. They cross areas of the moon. They can be straight. They can be wandery. And again, we don't completely know why they're there. Why are there lunar rills? Not quite sure. They could be lava channels where lava once flowed on the moon. They could have been lava tubes that collapsed. Not completely sure. Seen, though, in many images and by many astronauts. Going to the other end, this is a really small spheral. I didn't record the size. It's on the order of a millimeter, I would guess. This was gotten from the moon. Now, how can there be a glass bead, a spherical glass bead on the moon? Well, when meteors hit the moon, hit anything sometimes, it gets so hot that some of the rock and silicates fuse into little bubbles, and the surface tension for really small parts is so high it pulls it into a sphere before it cools. And so here you see this spheral, which is from the moon. And not only that, but this spheral has a crater in it. So you can see there's even smaller stuff. Moon dust, by the way, is mean stuff. If you're given moon dust, I'd back away from it because it hasn't undergone a lot of the erosion that Earth's soil has. So you can breathe in Earth's soil and it's not dangerous to you because Earth's soil has been rolled and wind blown and things like that. So all the hard edges, all the sharp edges of Earth's soil has been knocked off. Not true of moon dust. If you breathe in moon dust, it's going to stick to your lungs, won't be good for you. So stay away from moon dust. It's stuck to the astronauts' gloves, shoes, feet. Not their actual real feet, but their boots, things like that. It's dangerous stuff, lunar regolith. Okay, here's a more modern picture. Currently, the Japanese have a satellite orbiting the moon and mapping the moon, inspecting the poles. And here is a more modern picture of the Cayuga going over the lunar limb and seeing the Earth in the background. Now, how can this Earth be smaller than the other Earth? Well, it's a matter of magnification. If you were to zoom in on this picture, then this would be a larger fraction of the image. Back to the original image. So this is similar to where the people are on Earth. This is where the lights are on Earth. And this, as an email attachment, frequently says this was taken from the space shuttle, but it can't be taken from the space shuttle because, for one thing, the whole Earth is dark. How can you have the total Earth be dark? The other thing is there's no clouds on Earth. How can you have an Earth that has no clouds at all? What are the chances of that? Very little. This was actually taken by the DMSP satellites. They are defense meteorological satellites, and they're constantly, many of them are circling the Earth, taking images. And so what they do is they keep finding places on Earth from all the images that are taken. They cull the ones that are of interest to them. And those are the ones that are taken at night, and those are the ones that are taken when there's no cloud cover. And then what you do is you digitally put them all together. You superpose them with Photoshop. And then you get a picture of the Earth at night with no clouds, and that's what this is. And here you can see, the cool thing about that is you can see where the lights are. So again, the eastern seaboard of the United States is lit up. Houghton, Michigan is lit up if you look really closely, right in there. You can see where the people are because people tend to turn on lights. West Coast US, Western Europe, lots of people, lots of lights. Japan, lots of people, lots of lights. So India, I guess, is even brighter today, but not as many lights as one might have guessed. Again, if you want a nice dark sky, you might want to go into the Sahara, you might want to go to the Outback, you might want to go into the Amazon, or Hawaii actually is surrounded by lots of darkness, and so although it does have lights on some of its islands, it's actually a really good observing location. Also, this high up above the atmosphere in Chile is a really good observing location too. Okay, so now I will go to the astronomy pictures of the day. One thing I wanted to say, I don't know if I said, I did give out a clue as to what it would be on a quiz this week. So please come to lecture to find out a quiz question. I was surprised to learn that people aren't coming for the quiz questions because we pretty much have the same crowd as we usually do today. But let's see, we'll try this for another week or two. So you people in the audience might have, if you want answers to quiz questions, you want to invite people to come. Okay, so here we go. This is a planetary nebula called M57, the Ring Nebula. Now, the part that's usually seen, go away, is, sorry, talking to the computer, the text that came up. This is the ring part that's usually seen. So that's best seen with powerful telescopes. In fact, though, powerful telescopes only see really small parts of the sky. So amateur astronomers are now able to do something that is difficult for professional astronomers, and that's keep imaging on wide fields for long periods of time. Wide fields with small telescopes, just keep building up the image, and then you can see all this other stuff that you couldn't easily see with a big telescope, because the big telescope only wants to look at the bright stuff and only wants to take a small field of view. A big telescope, in order to find this, would have to do a lot of tiling and build this up over a long, many, many exposures. And that hasn't been done. So this is the Ring Nebula, finding out what's been emitted before the ring. And so our sun will become a planetary nebula at some point. Now, they're not called planetary nebulas because they're planets. They're called planetary nebulas because they might be mistaken for planets, but they're not. They are the outer envelopes of stars like our sun that were expelled when the sun was done fusing hydrogen in its core. And so our sun will undergo that one day. Here's a background galaxy that was just caught by chance. Okay, on to the next. All right, so this was a claim of a planet that was discovered. So here is a nearby sun-like star, and here was a planet. And so this was actually announced earlier in that week, and I avoided running it because I wasn't sure enough. I thought there was a distinct possibility that this could be a background star. There wasn't, but Jerry, who did this Thursday's APOD, decided this is maybe Friday's. This was good enough to go with, so we don't edit each other's choices except if there's some extreme misunderstanding. So we picked this one, so we're going with it. The thing about this is this is probably a Jupiter-type planet, or it could be just a binary star, and it's 330 times the Earth-Sun distant from its planet star. So it's thought to be 8 times the mass of Jupiter. So it's getting up near star mass, which we'll learn later in this course. And so this, if true, this needs to be confirmed. If true, this would be the first visually confirmed planet around a sun-like star. So we think there's lots of planets around other sun-like stars, but we don't know. So now we have visual confirmation, if this is confirmed, visual indication that this is true. So it's only 500 light years away from here. Okay, so there was a total eclipse of the sun in August, I believe. And so usually, as we see the big corona of the sun, usually you get images only of that much. But this person took 2 images of the same solar eclipse, one to get the inner part and one to get the outer part. And then he digitally put them together. So here you see the corona of the sun extending well out past where you usually see it. And not only that, but you can see the background star is much more clear. That's the M44 cluster, open cluster of stars, and we'll get to open clusters. Okay, running a little bit late here, so I'm going to go a little bit fast. So the day before the equinox was September 21st, Sunday, and there is a myth that you can balance eggs on their end. due to some forces balancing, but you can only do that on the equinox. But that's not true, because an astronomer who bills himself as the bad astronomer because he corrects bad astronomy to correct astronomy. He has a very popular astronomy blog now, which you can get to by clicking on that link, or just searching for bad astronomy on Google. He was showing here that you can balance eggs on end at any time. Now, when I first heard this, I thought it was impossible to balance eggs on end because I thought that eggs are completely smooth. But it turns out that even eggshells have tiny little bumps on them. And there's those little bumps that allow you to do that. You can also cheat and use salt, but we won't get into that. Okay, the next day, Monday, was the equinox, the autumnal equinox for the northern hemisphere. So here's where the sun goes in the sky when you're in the northern hemisphere, image taken every hour when it's dead of winter, when it's the longest winter day, the solstice. Here's the summer solstice, and right in the middle, or almost exactly in the middle, is the equinox. So these are taken once an hour, and so you can see that there's 12 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 is on the edges. So there's 12 hours at the equinox of daylight. However, in the wintertime, from this location, which was in Turkey, I believe, which is north of the equator, there was 1, 2, 3, 4, 5, 6, 7, 8, 9 hours approximately of sunlight. And then in the middle of summer, there were many more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 or so, maybe even more hours of sunlight. So we've passed the equinox, so now nights are going to be longer than days. And I'm running along, so I'll go. So last week, and reported this week on Astronomy Picture of the Day, a new dwarf planet was declared by the International Astronomical Union, and this one is a particularly unusual one. It's Haumea, and it is not perfectly circular. It is a triaxial ellipsoid, sometimes like an oblong. And we don't know much about it. There are only, it's only essentially a point of light, a barely resolved point of light telescopes. So it was discovered in 2003, and 2 moons were discovered in 2005 due to the ability of computer algorithms and clever search techniques to find things in the outer solar system. This thing is roughly the size of Pluto. In the long dimension, it's longer than Pluto. It's smaller in the other direction. It gets closer than Pluto, but goes much further out than Pluto. It has 2 moons. And the last one is today's Astronomy Picture of the Day. The sun has been unusually quiet. There's been very few sunspots, unusually few even for solar minimum, which is between the solar cycles as we are. But finally, in this past week, an active region came out on the sun. This is the first major sunspot region for many months. So it's exciting, and this sunspot is thought to be in the new solar cycle. And so a new cycle is beginning on the sun, we think, and the unusually dormant sun is becoming slightly more active. So we're going to keep watching that. Okay, so that'll wrap us up for today, and we will go out to Jupiter next lecture. See you then.